Welcome. First, I would like to introduce myself. I'm the nominated coordinator for injection molding processes at Hotset. And Hotset is a company which is located here in Germany, in Lüdenscheid. And we have a production in the UK and on Malta. And as well in the USA, we are producing electrical cabinets. And in India is a cable production. In Asia, we have some offices. And Hotset is known as a manufacturer normally for heating elements in any kind of variations and for thermal sensors. Maybe you know the hot slot and the hot flex, which are used in hot runner systems. And the normal cartridge heater, the hot rod, I think this is the normal heating elements we all know. When we put our components together, we're talking about systems. Systems like heating plates. We are increasing the temperature of big plates for any kind of processes. We have dynamic heaters for injection molding processes. And of course, our IQ system. IQ system is the conformal cooling and my theme for today. Our portfolio is the design of inserts, the heat treatment, the concepts inside of the inserts, and we provide vacuum brazing and, of course, additive manufacturing of the inserts themselves. I thought it was a good idea not to show you how they made the inserts. I thought it was a good idea to show you, here's this random inserts. I show you the difference between a normal insert in injection molding and one which is running in 3D. We make a simulation. At first, I would like to start with this insert. You know, this is a normal way, a conventional design of an inserts with holes are drilled that we have a circulation of the water onto the tips, onto the cavity. For example, here, this is the cavity where we have the plastic. And we increase now the insert up to 250 degrees, and then we cool it down for 10 seconds with 20 degrees water and see what is the result here. I start the simulation now, and here you can see we're creating hotspots which are produced by ourselves because we have no close to the cavity cooling. And after this 10 seconds of cooling time, we receive a temperature. The hottest temperature is about 200 degrees in the corner because it's the longest distance in the insert, and the coolest point is 110 degrees. A very big difference inside of these inserts. Let's save two values. Here we have a delta T about 90 degree in my insert. This is not good. If you're producing plastic parts and you have a delta T of 90 degrees, you maybe have problems with deforming of the part. Maybe the energy doesn't transfer to the insert into the water, and you have to extend your cycle time. Now we have another solution. Vacuum-brazed inserts, and here we took the solution that we're using copper inside for better heat conduction, for a better heat transfer. But what happens if we have the circulation of the water far away from the cavity, but we're using copper? What happens? Now the simulation starts, and we see directly there is no cool spot generated by bad circulation close to the cavity. It looks very homogeneous. The temperatures we receive here are not so cold as in the other insert before. We receive 235 degrees at maximum and about 216 degrees in the minimum. For my opinion, it is a good result, but we need more time because here is the delta T lower as in the example before. Okay, we doesn't reach the cold temperature, but the temperature of the insert in average is much, much better. So we are very homogeneous, but we have a bad heat conduction. Here we're using a 3D printed insert. This insert is running with a non-optimized temperature, and the circuits are integrated in the insert as best as I can. I don't know really what happens here. I try, and we will see what happens now when we cool it down for 10 seconds. What we can see here, there are cool spots as well as in the first example, but it is much faster. We will receive a maximum temperature of just 172 degrees in the corner. It is because, as in the first example, the circuit is too far away from the corner. We can't go inside there. But the difference, you see, 172 to 60 degrees is much higher, as in my first example. There was 90. Here we are about 110 degrees. Why is this happened? I'm using 3D technology. It must be better, but it isn't, because I forgot something. The temperature error. The temperature error describes that you have to take care how you design your cooling circuits into your inserts, because of the diameter of the cooling circuits themselves, and the distance between each other, and the distance between the cooling circuits and the cavity wall. If you don't take care of this example, you receive a high delta T on your insert, and that's what we see here, 110 degrees difference. This is an example for heating and cooling processes, because the energy transfer is absolutely the same. Now we're using an insert where we take care and balanced the temperature by using an optimized temperature system, and the cooling temperature control is much, much higher. We have a lot of heat exchanger surface in this insert here. And now, what is the result after 10 seconds? You see, at first, there is always a fingerprint of the cooling circuits. I will go back again. You see the fingerprints, but it comes homogeneous very quickly because the heat transfer is much higher, as in the examples before. Because the cooling circuits are balanced to each other, to the cavity, and we are running a lot of heat exchanger surface inside of this insert. Here we receive the temperatures after 10 seconds of cooling. You remember in the first example, we're reaching a much higher temperature in the corner. Here we actually have 68 degrees to 27 degrees, round about 40 Kelvin delta T, which means your plastic part after the cooling time is homogeneous cooled, and we reducing the stress inside of our parts. We call it controlled energy flow. You need to balance your cooling circuits inside of your molds. I have a little story. It is a nice story because it's just 1.5 years ago. We was on an exhibition, and a customer come to our booth, and the first words he's telling me was, "I am disappointed of additive manufacturing." And I thought, oh, why? Why that? What comes next? And he said, "During my injection, my melt is frozen." And I was a little bit confused. "Okay, tell me please more. What are you using? Just one machine, two machines? What happens there? What was the temperature?" And he said, "I'm using just one machine. I'm using the water from my cooling plant, as well as the other machines are running with normal modes, nothing special inside. And I'm running a 3D printed insert in this machine. And during injection, the melt was shocked by temperature, and it comes that the melt is stuck. He can't fill his part completely. And I said, you are disappointed because technology is working? He said the message, and I said, increase the temperature of the water. Yeah, he can't increase anything because in the other machines you get problems. You need to extend the cycle time and everything. And I said, okay, I give you one information which is missing. You freeze, you shock your part. Stop the circulation of the water during the complete injection process, during injection, and just open the valves when you are in the cooling time. What happens then is he's starting his process, inject the material on a higher temperature surface, and then he cool it down. He shocked it when the part is completely filled inside of his insert, and because of the technology, because of the big heat exchanging surface inside of his insert, you are able to transfer the energy from the plastic very fast into the water and freeze his part, but it's completely filled. And after that, stop circulation of your water. And he said, okay, I will try it. And he did it. And 1 week later, I get a call from him, and he said, it works perfectly better. I can reduce my cycle time. And I said, now, you have two opinions. You're running this insert in this way. You receive a cycle time which is better than your process before, or you're using this technology in all of your molds and increase the temperature of your water, which means if you're increasing the water temperature of your cooling plant, you save a lot of energy cost because maybe you don't need a compressor power consumption. You can do it by free coolers. And he do in a middle way. He split it, and after 1 year, he's one of our best customers for additive manufacturing inserts. I think this was a little experience of using 3D technologies in injection molding. It is a good solution, but you need to do it right, in the right way, and think about what's my aim. I said, thank you for listening. I'm open for everything. We don't have a booth here on the exhibition. You can contact us as well anytime. And maybe you scan the QR code or just Googling hotset.com. Thank you very much.
Thank you very much. It looks like it's a fairly well optimized process for the technology, the additive technology that's available to you. So there's 800 exhibitors at Formnext. What would you like to see when you leave here and go to somebody's booth that you think can really help you move to the next level with your products?
Especially us, I think it is, to visit this exhibition, it is an experience. You receive so many good ideas, your designs, technologies, the mix is so nice, and all the discussions we had here before on this day, I'm just visiting for 1 day. It is always nice, and we have some partners here as well on the exhibition, and it is always nice to be here. But maybe we are thinking about to be here in the next year, in the next time. I think this is a good idea.
So in terms of materials that are available to you, you're happy with everything in terms of the additive materials?
You mean the materials themselves is made of? Yeah, we're developing a lot because there is a hard competition in this area. Exactly for injection molding, it's very good to receive a good heat transfer inside of the inserts. And yeah, we are excited.
Okay, good. Thank you very much.
Thank you very much.